Welcome to NCREPT, National Center for Reliable Electric Power Transmission. This is the University of Arkansas 6 MVA Power Electronics Test Facility. So we support testing from a lot of our different researchers and a lot of our groups. Some of those groups that I'm going to talk about today are poets, seeds, and grapes. So we have our GRAPE Center, which is Grid Connected Advanced Power Electronic Systems, and we do a lot of testing for creating devices that make the grid more reliable and make sure that power is available at all times. So we do a lot of testing for them with regard to solar inverters, different distributed energy resources, things to make sure that whenever you come and turn your light switch on, you have lights. So we do testing for that group. We also do testing for SEEDS, which is the Secure Evolvable Energy Delivery Systems, and that's more of a cybersecurity focused initiative for energy delivery systems like the electric grid, as well as oil and gas. And then we also have testing for POETS, which is Power Optimization of Electrothermal Systems, and that's an interesting center where we're basically taking electrical engineers, mechanical engineers, and physicists and kind of putting them all together to try and find out how they can collaborate to solve current problems, especially with relation to energy transportation or electrification of transportation resources. And so what they're really trying to do is they're trying to shrink or miniaturize all these power electronic systems so that they have very, very high power densities. And when you do that, you have to get rid of a lot of excess heat, and you have a greatly reduced surface area. And so there are a lot of challenges there, but it's very interesting to hear through all these different lenses from the center for mechanical engineers and physicists and electrical engineers all finding ways to efficiently remove that heat. So just a little bit about our facility, our 6 MVA facility. We have 3 2 MVA circuits, and we have a grid simulator. So you can see the one-line diagram right here on the screen. And basically, we have 12.47 kV coming in from our distribution, and we step that down to 480. So we operate this facility at a nominal 480 volt, 3-phase, 60 hertz system. But we have this grid simulator, which is labeled as 3VF here, and that allows us to basically simulate a lot of different conditions for the grid. We can change the voltage magnitude, we can change the frequency, so we can simulate or emulate grid anomalies and variances. We also can emulate sags and swells and things of that nature. We have here 3 of our regen benches, and these are back-to-back converters, and they allow us to recirculate power. So whenever we're doing our large-scale testing, we don't actually have to pull 6 MVA from the grid. We can pull just a little bit, just our losses from the grid. To give an example of that, say that we're doing a test, and we have a unit under test right here on our medium voltage bus where it says EUT cell number 2. If we wanted to recirculate power, we would just basically command power to be brought in from this point at regen 3, and then we resynchronize with the grid and put it back out. And so we create a little loop here where we're recirculating power, and the only power that we have to pull is from the losses from that system. So we're very, very efficient, and also it makes us good neighbors, so when we're doing our large power testing, the lights don't dim around us. Put a little bit of context whenever I'm saying that we're a 6 MVA facility. A normal U.S. house, according to the DOE website, takes on the order of 1.2 to 2 kilowatts of energy on average, if you average that out over the entire year. This facility, we can test up to 6 MVA. So we can test a neighborhood, we can emulate an entire neighborhood of homes and how these distributed energy resources and such would affect those, or how the different inverters and everything would react to varying loads and varying grid stabilities. In the control room, this is the control room here. We have our main control computers, our displays, some of our servers and things of that nature, and we do all of our testing in this room. So we get everything set up. We set up in the Bay Area, and then whenever it comes time to actually do the testing, we can do everything remotely from here, because nobody wants to be next to some very high power electronics the very first time they're energized. So we have very strict safety protocols in place and a lot of protections and things like that. We develop test plans and checklists, and we can go through and step through these tests in a very safe manner, and we do everything from the safety of the control room. So if anything happens, we don't have any personnel in danger. In the control room, in addition to being able to control the entire system, we have monitoring. We also have an e-stop button. So if something does happen, someone presses that e-stop button, all the breakers in the facility open up. And we have those located next to all the exits, and we have remote e-stops next to every one of our test cells. This is part of our seeds test bed. So with all the power flow and all the realistic power that we have in the NCREPT facility, we can actually collect all this data from our protection relays and feed that into our seeds model or our cybersecurity models. But in addition to that, we also have this, which is additional protection relays, which we've integrated in with a hardware simulator, so a real-time simulator. And what this allows us to do, these protection relays and real-time automation controllers, they're very prevalent now in the U.S. So more and more municipalities and co-ops and distribution centers are using these protection relays because they increase the overall uptime. Previously, they were using electromechanical protection relays, where inside there was just basically a motor and a disc, and whenever you'd get an overcurrent event, they would turn that disc until it hit a certain point, which would trigger and open up a transmission breaker. That worked pretty well for a long time, but the problem is that you have small little spikes in current and things like that. You can start moving that disc little by little, and it might trip even whenever it's not needed to trip. You also don't have any way to kind of monitor that remotely. You just are notified when the transmission line is basically down. So with these have embedded systems built into them, and they can be connected up to the network, so you can actually monitor all these systems and kind of see in real time the entire swath. So that they have these systems for cities, for municipalities, but they also have them all the way up. They go into SCADA and ICS systems at the national level, so you can see the entire kind of energy status of the U.S. in one of these control rooms, which is very handy because it lets you kind of route power and such. As a lot of you know, it's very hard to balance all the generation and loads in real time. And so this kind of system helps you have that situational awareness so you can know when to bring on generators or when you need to reroute power. What we've done with the seeds test bed is we've built in these protection relays, and then we've created simulation models using MATLAB Simulink, and then ran them in real time. What a real-time simulator allows you to do is basically run a simulation. Say you have a simulation that lasts 1 second, it can run that simulation in 1 second. So a lot of times when people are running simulations, they might have a 10-second simulation, and it could take an hour to complete all the simulations and see what the results are. But with this system, using the optimization techniques and things of that nature, as well as FPGAs and multi-threaded processing, you can run these simulations 1 second for 1 second, so very, very, very fast. And they also have analog outputs, inputs, and digital inputs and outputs. And what we can do is we can interface this simulation with the real world. So we build a simulation model, like you see here on the screen, and we can run that and then connect these protection relays. Basically, we've bypassed the PTs and CTs inside the protection relays, and these relays now think that they are in the simulation. So there is not 9.3 kV at the back of these protection relays, or even at the PTs that would be connected to these, but these are reporting that they're connected to 9.3 kV, and they're pushing a few amps here right now, 17 amps. And now the protection relay is under the impression, basically, that it's running in this simulation, and all this data is being reported up to the real-time automation controller, which is then being sent out to the ICS SCADA, which is what we're looking at trying to protect from cyber threats and things of that nature. So we're going to show you a very quick demonstration of this, and we're going to have Stefano here is running a simulation, and he's about to cause a fault, and that'll be able to be seen here. You'll be able to see a lot more current running on this screen, and you'll see these protection relays kind of send the open command to those breakers. So as you can see it goes from 17 to 786, which is over the current rating, so it triggers the protection relays to open. Here we have our transformer yard. We have a 1.5 MVA transformer that supplies all the testing power for NCREPT. We have a 225 kVA transformer for all the house power, computers, control systems, things like that. And then here we have 6 of our 2.5 MVA transformers that are 15 kV voltage class. That means that they can take 480 volts and step it up to 15 kV, 13.8 kV, and then also step it back down to 480. This is what enables us to do medium voltage testing. These transformers are 2.5 MVA, 2.5 million watts, and they weigh about 15,000 pounds. So just keep that number in mind, because I'm going to show you another transformer here in a moment. These are our low voltage breakers for routing power throughout the test facility. Each one of them has an integrated protection relay, like we were talking about earlier, so we can actually sense and collect all the data from these devices. So we can sense voltages, currents, frequencies, power, things like that. I like to tell people whenever they come in that these breakers are very similar to the breakers that are in your home. The ones in your home are usually rated for 120 volts and 20 amps. These breakers are rated for 480 volts and 3200 amps at 3-phase power. So lots and lots of power available that we can route throughout the lab. We do have a lockout tagout system. So this is just a simple lockout tagout that we have. And basically what we do here is this is to whenever we want to make sure the lab is safe and no energy is flowing, we go ahead and rack out the breakers and lock them out so we can make sure everything's de-energized. So this is representative of our regen benches and grid simulator. This is a standard back-to-back converter, custom built. Each one of these switching positions that you can see is the white rectangle is rated for 2,000 amps. So in each switching position we have 3 of those, so 6,000 amps rated for each switching position. With these we can do grid simulation, vary voltages and frequencies, but we can also do the regenerative testing we discussed earlier. Now all this comes back, you can see the gate drivers, fiber optics which trigger the gate drivers, and all the fiber optic signals come back to this. This is the overall control panel of this. It has FPGAs and DSPs, and we can reprogram that so that we can emulate various distributed energy resources in the lab. All right, so over here we have our dynamometer, 100 kilowatt dynamometer test stand at NCREPT. We built this so we could have a very realistic testing environment as we're developing all these motor controls and motor drives for transportation applications. And our researchers wanted to have very realistic environments. So we have a thermal chamber that can go from negative 75 degrees C all the way up to 175 degrees C. We have 105 degrees C coolant loops for cooling the power electronics, silicon carbide power electronics. And then we also have an actual dynamometer. So instead of just running into a resistive load, we actually have motors that are connected together, and we have one motor drive which supplies a specific torque to the shaft of the motor, and then the motor drive under test controls speed. So you can see here we developed this control interface such that we can control all the major components. You can see on the tabs here all the major components for this test stand, and then we automated it. So we spent a lot of time on this. We were very proud because basically we got it down to the point where we could just read in a CSV file and it would run a 3-hour test with us just clicking a button. Everything was automated. We would sit down, turn the system on, press the start button, and this control center would just go through, set a certain speed, and then go through and stair step through all these torques for 30-second intervals, and then it would collect data at every one of these points so we can analyze it later on. And so, tests would take about 3 hours. It would go through a certain speed, step through the torques, and then go ramp up to another speed and step through the torques again. And we're able to collect a lot of great data, terabytes of data, create nice efficiency maps, things of that nature. And we were really happy with it up until one of our researchers came to us and said, this is great, collecting all this data, have the whole system automated so you can just press a button. But I have to say, we did all this so it would be as realistic as possible. And with thermal chambers, high temperature testing, things like that. But whenever I get out on the interstate, I don't apply 20 Newton meters to the shaft of the motor in my car. It's a lot more dynamic than that. And so we started thinking, what, you're right. So we had one of our master students spend a summer and some of the following semester developing a virtual vehicle. So they're using the Opal RT system, the real-time simulator that we had discussed previously for the cyber activities. They actually developed a virtual car in this real-time simulator and then had this virtual car drive the US 06 driving schedule. Same type of EPA driving schedule that you would get whenever you go to like a used car lot or any kind of dealership actually, and you looked at the sticker on the window and it told you what your miles to the gallon were. That same driving schedule. So we had this virtual car running this driving schedule, and in real time it would send the torques and speeds that were seen at the shaft of the motor to our dynamometer test stand, so it could then emulate that. And so instead of these nice, relatively straight curves that we're seeing here, this is the much more realistic version with much more dynamic signals showing the torques and speeds for that US-06 driving schedule. So this is our 1.5 kV DC power supply that's rated up to 2 megawatts. Basically, as we're doing our solar inverter testing, especially for grape, there's an increasing trend. 10 years ago, very common for solar inverters to operate with 600 volt DC input from solar panels. Now it's very prevalent for 1000 volt DC input, and as we're trying to press efficiencies even higher, one way to reduce the losses is to increase the input voltages so you can reduce I2R losses. So now a lot of solar inverters are actually going to 1500 volt DC. Well, we didn't have a 1500 volt DC power supply at the time that could achieve these power levels, and so we started looking into it, and it was going to cost around $2 million and take 9 months to get one of these supplies installed here at NCREPT. And so we decided, okay, we'll just do this ourselves. So we invested approximately $100,000 in parts and such, and then a good bit of student time. But we had the students actually go through, students and engineers, go through and design every part of this and fabricate a lot of this. And this is now a 1500 volt DC power supply that's available in our center. Previously I was showing you those 2.5 MVA transformers. Remember, those they're 2.5 megawatts, right, MVA, and they weigh 15,000 pounds each, so very heavy. This transformer is 3.5 MVA, so 3.5 megawatts, and it weighs on the order of 300 to 500 pounds. So a significant reduction in size. And the reason for that, the primary reason, it is water cooled instead of oil cooled, but the primary reason that is so much smaller is because of the reduction in magnetics with regard to frequency. So those transformers out there are operating at 60 hertz. This transformer is operating at 1 kilohertz. So going from 60 hertz to 1 kilohertz, you get that much of a reduction in size. That's one of the reasons why we're focused so much here and with our centers in pursuing silicon carbide, because you can really have much faster switching, and that allows you to greatly reduce the size of the magnetics, and that allows much lighter power electronics for things like planes, trains, and automobiles. In 2017, we actually expanded our facility from 7,000 square feet to 12,000 square feet due to all the increased projects and activities that we've been involved with. Part of that expansion, we needed to actually go through and reprogram our PLCs, basically the brain of NCREPT, such that it can accommodate the new breakers and the new peripherals that were being installed in the facility. It was going to be cost prohibitive to do that, though, so what we decided to do was go ahead and purchase a PLC and put it in and program it all ourselves. So that's what you see here. This is actually one of the most cyber secure PLCs on the market today, and we're doing this as one, because we want the capabilities to be able to program and reconfigure our facility as needed down to the PLC software, but also so we have a very nice cybersecure interface for our seeds researchers to do additional testing on. So this is just another example of something we did here at NCREPT. We needed a 650 volt DC power supply that was rated up to 700 kilowatts, and we didn't have anything like that at the time for this particular test. So what we did was we retrofitted an old motor drive that was donated to us by a motor manufacturer, and we basically reconfigured the entire cabinet, designed and installed our own sensing and control circuitry, and reprogrammed this. So this used to be a 3-phase motor drive, but now it's actually a dual interleaved buck converter that can go from 0 to 650 volts DC up to 700 kilowatts.
So this is just a couple of examples of some of our student projects. These are 2 chillers we have, and previously this heat exchanger would just basically run off of line voltage. You would plug it into the 208 plug, and it would run at whatever line frequency was happening right then. As we're doing more and more of this of testing of silicon carbide inverters for energy like grid connected and transportation applications, we need to know more precisely what the coolant is, and we also want to be able to control the flow rates. So what the students did over the summer was they integrated a PLC that also included some pressure transducers, temperature transducers, and a flow sensor, an ultrasonic flow sensor, as well as a motor drive. And so now, instead of just having to plug this into the wall and getting whatever, we can actually sit there and remotely control all of these devices and collect all the data remotely. We also replicated that over into this 105-degree-C coolant loop, so we can again control the flow rates very precisely, monitor and collect all the data, and do it all remotely. So it's just one of those kind of neat experiences that the students get here at NCREPT. So this is the MVUCSC project that we're testing here. This was fabricated at NCREPT, and we're doing some 13.8 kV testing on it this week. So the main purpose of this project is to kind of rebalance grid currents. So a lot of times people will have feeders in the distribution system, and they'll break off and feed a lot of single phase loads like homes or things of that nature, and those currents get unbalanced, which minimizes how much power can actually be transferred. So by rebalancing at the transformer using devices like this, we can actually maximize power transfer for the system. This system here is a 700 kilowatt AC load bank that we use in testing the MVUCSC project.
So this station is our CNC station. Really happy to have this. Allows us to do things like fabricating copper bus bars, enclosures, things of that nature. And we're also doing a lot with it with our packaging work, being able to machine graphite fixtures, different holders and fixturing and things of that nature. Really does help accelerate our research. So the Tormach allows us to create enclosures like the ones seen here and being shown in the simulation here. So this is actually an enclosure for a power electronics eval board and a top that we did over the summer. Our CNC mill has a lot of nice accessories such as a lathe and a fourth axis. So really enables us to do a lot with this machine. So these are just a few examples of the pieces that we've machined. So this is machining some copper tabs for a project which were adhered to this aluminum plate. We have, again, the PE valve board enclosure that was machined over the summer to give the electronics a nice, safe, cool place to rest. We machined some bars for a thermal interface that we built up. And then we also use other machining tools. So in addition to copper and aluminum, we've been investigating more in ceramics and also graphite. So this is actually a graphite fixture for high temperature sintering and such. And this little fixture, graphite fixture, is for adhering solder balls onto a bare die.
So these are medium voltage breakers. This allows us to route power throughout the lab at the 15 kV voltage class. All of these are also outfitted with protection relays, so again we can collect all the currents, voltages, and grid anomalies as we're testing.
As part of the 2017 5,000 square foot lab expansion, in addition to the 4 additional testing bays, we also added approximately 1,000 square feet of student office space. This space gives a comfortable area for our associate students to work and collaborate on their various projects. Thank you for taking the time to learn more about the NCREPT facility.